Right, I tried to make this video earlier on a different computer, but the flipping thing crashed on me. It was overheating. Right, okay, I'm going to try again. If I can get this preview a bit bigger so I can see it. Anyway, somebody twisted my arm um, to make a video about my upgrades I did to my inverter, and I'm just going to show you something. Now, most of the cheap inverters on the internet, on eBay, the quality is, well, leaves a lot to be desired because they usually blow up as soon as you put a heavy load on them. And the reason is why is they use this pretty cheap rubber thermal foam, well, thermal rubber type, and it's impregnated with heatsink. I've got some muck on my fingers, you can see there. Heatsink bonding. Now the problem with this stuff is it's not very good, it's not very conductive thermally, and it's also not that great with electrical high voltage either, because it can break down, especially if you have to get holes in it. Now what I wanted to show you here, or rather what you really need to know, is how to improve your inverter. You should be able to gain anywhere between 15% to 30% improvement in performance. That is, it won't blow up on you if you put a bigger load on it. Now, instead of using that rubber stuff, what you need to do is get your hands on some ceramic insulators and thermal bonding. Now, this ceramic is well known. It has a long history of being ideal for conducting heat, because that's why you use it in electric and gas fires. And also electric fires, if you ever take them apart, you'll find out that the coil is wound around ceramic. And it's because it has good thermal properties in conducting heat and radiating heat, which means it's also excellent as a heat sink. It's been well known for a long time actually, and I've discovered there's some websites that are now manufacturing ceramic heat sinks which are even better than aluminium. You know, you gain up to something like 30% extra thermal conductivity. Now I've got two of these here. You can buy them online. I'll show you in a moment if I can switch over. They're not cheap. You're talking about something like £2. I think it's £1.60, about $3 a piece. But it's well worth it if you really want to boost the quality of your inverter. I'll just put these down here a minute. Now, there's one problem with these. This particular Doxin inverter, when I bought it, the ceramic heat sinks wouldn't fit in. If you look down here, I've actually got two fitted in there now. Let's see if I can get this angled so you can see it. Right, if you look closely, you'll notice I've got two ceramic thermal bonding discs, pads actually you can call them, behind those MOSFETs. Now I've also let me turn this around. I also got 4 more on the high voltage side, because they're very good in high voltage situations. Very good insulation, both electrically, and very good conductivity regarding heat. So the problem was that these ceramic discs, if you look at the ones at the back, look closely, you'll notice that they're all bunched up very close together. They have to be like that in order for them to go behind all of the MOSFETs. Now the problem was the bolts the bolts that clamp these metal brackets here, these metal brackets to clamp the MOSFETs to the heatsink, couldn't find a way through. Oh, I thought, oh dear. How am I going to get these ceramic pads in there and also have room for the bolt? Well, that was my problem. There was no room. So what I had to do, what you have to do, is invest in one of these. It's a diamond hole saw. It's a diamond cutter, because you can't drill ceramic. It's extremely hard. Extremely hard. You've got no chance in drilling it with a conventional drill, so you have to go and buy one of these. They're cheap enough actually. This is actually a 6mm diamond dust hole saw. Now I actually got the wrong size. I should have gone for I think it was a 3mm or 4mm, but anyway, it did the job. So if you go online and go on eBay, look for a diamond hole saw, and you'll need to make holes. Now the way you do this, now let me just show you that let me just get my pen, make this a bit easy to see. Because of the way the bolts on the Doxin are positioned and the clamps, if you look inside there, because of the way the bolts come through, it actually goes right through between the two MOSFETs there. Right in between. So what you have to do is, I'm just going to mark this and show you what I did. I actually had to mark it up, but you'll have to mark it up yourself as well. Get yourself some of this ceramic. You can find them on eBay. What you have to do then is, I've made a red circle, right, where the bolt would go through. I'm moving them up and down so you can see. The problem was the red circle, the hole had to be across both of these ceramic, half a moon on one side, half a moon on the other. So what I did was I got myself some wood and I put a piece of wood across the top, and I put a piece of wood around the back, and then I clamped the whole thing up in a vise. Now you have to be careful, because remember, ceramic is extremely hard material. Doesn't mean to say you can't break it, because you can if you put too much pressure on it. So that's the reason why you need to use wood. So get your wood, place it around the bottom half and on the other side, clamp it just tight enough so that when you try to move it, it won't move. Next step, because these hole saws don't have a centering pin, when you try to drill a hole through ceramic, let's just get this on here, when you try to drill a hole to make it possible for you to put bolts through, the cutter's going to drift all over the place. Also, you have to use liquid to cool it, so I would suggest you don't use a high power electric drill. Use a mini drill, one of these mini drills. I adapted mine. If you look, I put a thin shaft and I inserted it into the larger shaft. I use epoxy resin to bond the two together so I could use it in my mini drill, because they actually come with a rather large shaft on them. Once you've got this clamped up, what you have to do is you have to make a guide, a hole guide. The best way to do that, let me just make a hole in this foam. Maybe I can show you what I did. If I can just get this through. Right, okay, I pushed a hole through it. Right, I made a hole in this rubber foam just to show you, but you would use something like wood, or you could use metal. What you then do is when you clamp this up, into your vise or whatever you're clamping it with, you have to clamp your guide You'll need to clamp your guide as well. Preferably use the same piece of wood if you want. The wood that you're actually clamping it with. Now that you can use that hole in, if you're using wood, I'm using foam because it's easy to handle on here, but you can use that as a guide for your diamond drill, diamond hole saw, and then when you're cutting your hole with your diamond hole saw, it will keep the hole saw centered over the in position over the ceramic, and also put plenty of water. You know, just get a syringe used for filling cartridges, ink cartridges. That's what I did. Just get a syringe, put a bit of soap in it if you want, liquid soap if you want, just to lubricate the diamond, because this powder stuff, the diamond powder on the drill, it doesn't like getting any heat to it. If it gets too hot, it can melt the bonding that's holding the diamond dust onto the cutter. If that happens, then your drill's going to be completely ruined within a few minutes. So keep it cool, just do it slowly. Now these, let me just switch over if I can do this. There we go. Now you should be able to see the ones on eBay. They're actually different to mine because I actually got mine off out of an old high voltage sunbed PCB which was designed to run tubes. Now there you go. There's the ceramic pads that you can get, and they're about £1.50 each, and you can get them from Sign Quan on UK. Now it's got a good rating, 99.9% positive feedback, so I recommend you go there. They're not cheap, but it's well worth the investment. Now, to explain a bit more about ceramic. Now my good friend, well, it's not really a friend, I don't know you that well, do I, Julian? But Julian Eilert, he's got a great YouTube channel, and he's talking about all sorts of upgrades and developments and circuits, and he's got a YouTube channel, and he's been reviewing some of these MPPT charge controllers. Now let me just jump over to, there we go. Now, innovative thermal management with ceramic heat sinks. Now that is what you want to go for. These ceramic heat sinks have something like a 30% improvement in thermal conductivity, much better than aluminium. Also, you've got a benefit there of not losing efficiency in any of your projects, such as LED lights. They're mainly designed for LED applications, but there's no reason whatsoever why you can't use these heat sinks in other projects, such as inverters even. They have extremely good thermal conductivity, so don't be surprised if when you build something that from the outside it feels like it's getting a lot hotter than it used to do. That's only because it's conducting more of the heat away into the heatsink. Right, there's different types of ceramic. There's aluminium nitride. There's actually a PDF you can get. Now, let me just see if I can find this. Now, as you can see from this, let's get this the right side. Ceramcool, the ceramic heatsink for efficient thermal management. Now, all gas fires are use ceramic radiators, by the way. I don't know if I mentioned that earlier. But also electric pylons, or the top of high voltage pylons, they use ceramic insulators, and they also conduct the heat away from high current cables. So they've been using them for a long time. It's sad though that it's very hard to find on eBay, but you can find them, I believe. But this seems to be quite specialised, and I don't think they're going to be cheap. So let's just read this. It offers a strong solution for thermally sensitive components and circuits thanks to its excellent thermal conductivity and stability characteristics and its compact form. Ceramcool is the ideal heatsink for high power LEDs and high power electronics. Simplification and miniaturization for high reliability. Now, I'm not going to read it all because you can go and read it yourself. Just search Ceramtech. The company, Electronic Applications Division, I don't know, I'm not sure where it's based actually. But there's a website. Now you click on the website, and that's the one I was just at there. It's Ceramtech. And if you go click on products on the website, there you can see you go down, I think it's about here, there's the heat sinks, that's where I was before. You can look at the heat sinks, and there's one other good advantage to ceramic heat sinks is that they don't corrode. They don't corrode, and also they don't short out like aluminium, so you don't have to worry about any more pads or separating your components. You can just bolt them or clamp them directly onto the ceramic without any worries about any extras. Because what they're talking about in here, let me just go down. What they're talking about is basically is that go back to the PDF. Is that basically what you have normally is you have your component, which might be your LED. Then you've got your PCB substrate, and then you've got your conductor, then you've got your glue, and then you've got your heat sink or whatever. So I mean, you've got a lot of losses. Your heat dissipation is lost through all these various things that you've got in there. But because you use because of the Ceramcool is basically just LED straight onto your ceramic heatsink. It says up here, typical LED system with multiple layers and different TCEs, potential risks, delamination, corrosion, degradation, and a simple and small LED system with Ceramcool, optimized thermal management with direct metal to metal connection. Main advantage, excellent long-term stability and high reliability. Right, okay. Go over here. There are all sorts of different shapes and sizes. Anyway, I'm not going to waffle on about all this because the video is going to get too big. Just basically have a look on eBay, see if you can find it. If nobody's supplying these ceramic heat sinks, then maybe people need to be doing that. But the PDF, you can find that if you just search, let's see, Ceramcool heatsink. That's Ceramcool_heatsink.pdf. You should be able to find it online and do some reading, because I tell you, the inverter, let me just go back to my inverter now. Right, okay. Now, back to the... Now, when I first got this off off eBay, what happened was the capacitor, which is, there was one single capacitor of 2,200 microfarads in here. It blew up. Well, it obviously would. As soon as I put any extra load on it, it blew up. So what I've done is I've actually wired 3 capacitors in parallel, and each one's 1,000 microfarads. So there's 3,000 microfarads. Now, some people were talking about don't have the legs too long. Well, that's a load of bullshit, sorry, but that's bullshit, because these capacitors are basically wired across the power supply that's coming in, so that you're coming in on long wires anyway. Now the trick is to have decent capacitors, wire them up so that the legs are quite strong enough to carry the current, and you can instead of having one which takes too much load, and mine was blowing up, and just to prove it, this is a brand new, this was a brand new 3000, let's got it right way up, 3300 microfarad capacitor from China. I put it in, it was working, and as soon as I put a 300 watt load on this inverter, the thing fried. Well, the capacitor started to bulge, look. Let's see if I can get that on. It started to bulge, and it was only in there for 10 minutes. So I immediately took the thing apart, took the capacitor out, and I thought, well, that's no good. That was a 3300 microfarad, it can't even take a 300 watt load. So I took that out, and instead I wired three 1000 microfarad capacitors in parallel, so that I had 3000 microfarad connected. Now also there was one that was a bit smaller, so what I did was I made a heatsink, which is it's hard to get this right. There's a heatsink here which I made out of a piece of thin plate, which I wrapped around the small capacitor at the bottom and directed it into the airflow so that it actually keeps the capacitors cool. And I also fitted a thermal fuse, which is it's a momentary, as in it reconnects as soon as it's cooled down. I also fitted a thermal cutout fuse against the capacitor, which is wired in series with a power switch, so it basically turns the inverter completely off if the capacitors overheat. I've also got another thermal monitoring, I don't know if you can see that, turn it around, on the input MOSFETs down here. There's, I can't get this in now. Right, on the input MOSFETs, I can't see what I'm doing. There's a thermal thermistor mounted up against the MOSFETs there. Now what I've done is I've also got another thermistor which I've clamped, I've stuck right against this bracket that holds the MOSFETs against the case, and this controls the little circuit board which I put in, which is thermal fan speed control, and it controls the speed of the fan. And it's a simple circuit you can build. All it basically is a single transistor biased with about something like 20k, or about 30k, 33k, and what you do is and it's got pull down resistor of about 3.9k, and what happens is the thermistor, as it gets hot, it biases the transistor heavier, and the simple collector to negative pin of the fan, and it pulls the power through the fan and speeds the fan up. So instead of having a noisy inverter running 24 hours, or if it was 24/7, it only runs the fan when it really needs to run it. So for example, most of the time it's not wasting power running 150 or 200 milliamp electric fan. It's not wasting that power. Instead it runs down to a trickle. Now the fan actually is the standard one in this one. I actually had to put another fan in my other one because it was too noisy. It was just too noisy, and that's basically it. Well, I've used these ceramic pads on all of the MOSFETs, all of them. Normally you only need to use them on the high voltage side, but because of the thermal benefit, I decided to use them on the input side, the high current side, which is where the 12 volts is driven straight through the transformer. So you can use them on all of them, all of the MOSFETs, but they're just quite a lot of money. I was lucky, and I'll explain why. I had these board given to me. This is a high voltage. It's designed to run. It's a big board. It's designed to run sun lamps. And if you look, you'll notice they've all got these ceramic pads, insulators, for good thermal conductivity. All of these MOSFETs have them on this panel. So it's not new tech, it's old tech. It's been around quite a while, and this is an 8-channel sunbed driver. So I was quite fortunate really to have a load of these for free, and it hasn't cost me a penny, but you know, you can get them off eBay, that's a good thing. So they've been widely used in industrial equipment for a long time. I'm just surprised that we don't see them more in domestic equipment more. Anyway, that's basically all I need to say. As I say, I'm going to put this back together, and I'll try and demonstrate this actually how well it works, and you'll see for yourself. So I'm going to stop the video because it'll take me a while to put this back together. Okay, right, I've got my 300 watt kettle. Let's just I've just emptied the water out into a container so that I can, I can't get the camera right. I need to get a better view. I'll move the camera. Now it's really ideal is this, because it's a small kettle, and if I can get this on screen, let's see. It's not very easy to get this. I don't know if you can see that. 300 watt kettle. The light's a bit reflecting off it. It's Sincere model S022, I think it says. 230 volts AC. Let's see, I'll just get closer actually. 230 volts AC, 50 Hertz, 300 watt, and that's my kettle. It's got a little light on the front. It's called a Linette. There you go. That's it. Right, I'm just going to put this down. Put my water back in. Now I'm not going to put much in because I don't want to run my battery down just for the sake of it. Plus it's going to take a long time because it's only 300 watts, so don't expect it to boil the water like lightning, because it won't. I've got my new battery, which, you know, my solar battery I was telling you about. I know I made a video about the big beastie. Oops. Right, well, that is running my inverter at the moment. It will do when I switch it on. Right, get my kettle. Let's see if I can get this camera a bit higher up. Just a moment. I need to elevate the camera a bit. Right. Hopefully we can get everything in. Right. The inverter, I'll move the plug the other way around. It's the Doxin Inverter which I upgraded. Let's get it right way around. Okay. Can't get it all on. I'll move it around a bit. Okay, right. I want you to see the steam so that we can get it working right. I'm just going to unplug the kettle a minute because I want to switch my inverter on first. Power up. There we go. Inverter's running. Don't know if you can hear that. Right, let's plug the kettle in. The kettle is lit up. Let me just turn the light out. There you go. Now listen to the inverter fan. And the wires are getting warm. Let's watch the water. So as the heat starts to go through the transistor down here, it's picked up by the thermistor and the fan just revs up, which is the way it should be. I'll just lift it up a bit so you can hear. Oh, the wires are getting really hot now. I don't want to melt them. Yeah, pan's pulled, maxed out now. And my wires to the battery are getting bloody hot. Put it down because I don't want to. And the heat sink, the heat's been dissipated very well. In fact, it's bloody almost impossible to keep my finger on there because it's very hot. Revving up, which is a fan control, speed fan control. My wires are bloody melting. I hope they don't. You know, the low voltage 12 volt wires that are quite thin actually, they're bloody getting hot. Now, can you see the kettle? Can you see the steam? Hang on, tell me loud. If you can see that. Let's get the other light around. Let's turn it around a bit. Can you see that steam? There we go. You can probably hear it. And my wires are very hot now. The inverter is having a breeze, hardly working. Right, just want to get this boiling so that it turns itself off. Move my other light around a bit actually. I think my 1000 microfarad capacitors are actually doing their jobs quite well. There's a lot of heat coming out of here, out the inverter at the back, so it's definitely working. And the inverter's quite hot now all the way around. It would probably be a bit quicker if I'd got heavier duty cable on the input to the inverter, because I'm actually using fairly, I think it's only 10 amp cable actually, but it's doing quite well. And look at this steam off this. Oh, I can't see that. Let's put the light on again. It's bubbling. Oh, there, it's boiling, look. Look at that. Yeah, it's turned itself off, look. It's boiling. So there you go, and the inverter should start to slow down by itself as soon as that temperature starts to drop. just to lift it up again. It's bloody hot. Should start slowing down in a minute. I'll turn the kettle off now. I don't want to run my battery down. There we go. Slowing down. It's actually cooling down quite a lot now. And the fan speed control circuit, if you want to build one, all you want is a standard thermocouple, which you can get off eBay. 20, I think it's 20 kilo ohms. Yeah, that's the one I used. Actually, get a couple of, and wire two of them in parallel. The reason for that is you get a much faster speed uptake with a fan as soon as things start to heat up. Put one thermocouple close to the the main input power transistors across the 12 volt driver circuit, and put the other one on the capacitor, the one that's on the power intake, because that thing does get hot, and a lot of people have had blown capacitors, so you want to clamp it on with some thermal tape. Actually, this is what you want to use. Let's see, you want to use some of this. It's Captain tape. You can get it up from, well, it's actually from China, a lot cheaper. It's fireproof flame retardant tape. Just to show you what I mean, I'll get a little piece here. Oh damn it, it's stuck on my sellotape as well. If I can get it. Right, here's a bit of Captain tape. Right, and if I get my lighter, if I can find the flipping thing. And if you heat it up, ooh, that was the sellotape that was stuck on it. But it is heat proof. It doesn't burn generally. It's fire retardant. Captain tape is what they use in power transformers. I think I had something else on there actually, because a bit of sellotape got stuck to it. But it's fire retardant. It doesn't burn. It doesn't burn by itself like sellotape. Now forget sellotape. Now, you know what sellotape's like. I don't want to burn my fingers. It shrivels up. It shrivels up really quick, sellotape. Whereas Captain tape doesn't really. It's designed to insulate transformer windings actually. But that's what I'm using on the to bond the thermocouples onto the capacitors and onto the on the other components that get hot generally. So you're very wise to use. Anyway, as you can see, it's slowed right down now, so that's cool. But I have still got hot boiling. It's probably still steaming actually. Don't know if you can see. Let me move the camera again. This camera's got a mind of its own. Yeah. Right, it's still steaming there, look. Anyway, so just basic how to upgrade your Doxin or your other inverter and get better thermal conductivity. Just go on eBay and get some of them. Sorry, I'm half asleep today. I keep forgetting what I'm saying. Get some of those so I make discs. My age is showing, I think. Okay, thanks for watching. As I said, I don't really like making YouTube videos, but yeah, I hope you benefit from it, and you can give me a thumbs up if you want, but I won't be offended if you don't. it occurred to me that there might be some people who are interested in my speed control that I made for the fan. Well, it's a really simple circuit actually. There's nothing much to it. All you really need, it depends on what you want to monitor, but the way I did mine, because I took all them battery packs apart, I had loads of thermistors. Sorry I don't actually have the correct symbol here. It's not the correct symbol actually, but I'm actually using a different symbol. But what you need is some of these thermistors. You can buy them off eBay. Now there's different types, so as long as it's a 20k, because that's what I'm using in my circuit. Oh, hang on a minute, go back. Now there's other types. There's NTC thermistor 20k, they're cheaper. Oh no, actually post and packing for them as well. But all you need is some simple thermistors, about 20k, and that is that the resistance should drop as they heat up, right? So you need the ones where the resistance drops as it heats up. Right, there's lots of them on eBay. There's different types. There's surface mount. Right, anyway, let's get back to my circuit. Now, all you need is to do to monitor is, I'm using one thermistor to monitor my capacitor on in the inverter for the temperature, and I'm using one thermistor to monitor the MOSFET. I've actually got 3 in mine. Actually, I didn't. In my other inverter, I've got 3 actually, but in this, the one I showed you, I've only got 2. But you can have a third. Now, the way I'm doing this circuit here, let's just zoom in a bit. Let's just move it around. Now, this circuit, let's just connect this to that one. I'm using a capacitor. Now, the reason for that is it's to kickstart the transistor and the fan when it's cold, because when you first power the inverter up, there's not enough juice to start the fan, and it usually starts off in a stalled state. So I'm using a 100 microfarad capacitor because it gives me a bit longer duration. Connect that to another thermistor or a static 20k resistor. It's up to you. If you want an extra thermistor in there, then replace the standard 20k thermistor with a 20k resistor, right? And that pushes the BIOS to the, oops, I haven't connected that one for some reason. Let's try that again, as it's supposed to be up here. Oh, it's this one here. Right, okay, so there we go. Right. Now this is an NPN transistor. It's a BD131. Now, the way we're doing this is emitter is connected to ground. This software sucks because I haven't put my power rails in, have I? Right. The pull down resistor is a 3.9k, which is what I'm using. Let's just try and get this hooked up. Right, that's the pull down resistor for the base of the BD131. And as I said, the other thermistors are actually connected in parallel. So let's just get these hooked up, and they're connected across to let's see, let's get this all done. Right, okay, right, well, I've got a kickstart capacitor which is connected across these 2 thermistors, so that, and it actually goes through this 20k. And obviously the way I've set this up is the collector goes to the negative. This collector goes to the negative what connection on the fan, because it pulls the fan on by pulling the negative terminal of the fan to ground. An emitter goes to ground. R1 on the other end goes to ground. Right. So your positive of your fan goes directly to supply, and these resistors here and the C1, the positive terminal of C1 goes directly to supply as well. Right, so when power is initialized, the C1 energizes the circuit with a pulse, which basically momentarily turns on the BD131 transistor full on just to get the fan started. And once the fan starts, then it goes back to a slow speed and a trickle speed. It's a very, very, very simple circuit. There's not a lot to it. I mean, I'm just going to stop this video a minute and I'll try and fill it in a bit more for you, so you can copy it and then you've got somewhere to work from. Terminal, yeah, okay, that'll do. Right, this'll do. Right, I'll stick some terminals up here. Right, there's 1, 2 positive, and there's 1, 2 negative. Alright, let's just connect these up. Right, the fan's going to be connected to these terminals. Oops, wrong one. I want to connect this up to the supply. There we go. Right, okay. Oops, too much. Let me just get rid of this and minimize it. I'll just hide that a minute. Right, okay, let's just get this bigger so I can see. Right. Now, there's our circuit. Basically, you've got your 12 volts power input. Now, there's a little trick I'm going to tell you. What I actually noticed with the inverter was that when it was running, the voltage was dropping and the fan was slowing down. I thought, oh, this is ridiculous. I want the fan to run faster when it's getting hot, right? When there's a load. I thought, how can I do this? Anyway, I came to the conclusion that the actual driver circuit, now if you look in the inverter, you'll notice on the transformer windings there's 2 real thick heavy duty wires that go in to the windings. It's a center tapped transformer, right? You've got your tapping for your one winding, and then you've got your center tap, and then you've got your other tapping for the other winding, which drives the transformer in the inverter. Now, there's a little trick which I did on mine. What I did was I got a full wave bridge rectifier. That's 4 diodes. A full wave bridge rectifier. I connected the AC connections of the bridge rectifier, one to the farthest tapping of the transformer. Don't touch the center tap connection whatsoever, leave that alone. Then I connected the other AC connection to my full wave rectifier to the other tapping on the transformer, and basically there was about 30 volts. I was thinking, no, it's about 25 volts, something like that, around 18 volts actually. I think when it was loaded, there's about 18 volts across that winding. I thought, brilliant. So what I did was I built a simple little circuit using a 12 volt regulator and a bridge rectifier. The bridge rectifier takes some of the voltage from this high current device input to the transformer, which, I mean, it's a high current input, so I mean you're not going to really be significantly taking a lot of power from it. So then you feed that into your 12 volt regulator, which you wrap up in heat shrink wrapping and insulate it. Then you drive this fan circuit directly through the 12 volt regulator. That way, when the voltage drops on your input to your inverter, you've still got a stable 12 volt to run your fan, and your fan isn't slowing down. And it worked really well. Now I could go and explain all that to you, but I'm sure you'll be able to figure that out. It's a standard bridge rectifier, full wave, and a 12 volt regulated IC. You know, simple in, ground, and out. That's all you want. It's a 3-pin device. Let me just pull that up if I can find it. I think it's one of the LM series. LM, I think it's LM 12, let's say 12 volt reg. Should find it on here. Alright, there you go. Right, all you want is something like one of these. It doesn't have to be high current. LM3210, let's see, I think it's pretty much. Right, okay, there's lots of these around. You have to look up the specs for those yourself. But anyway, all you want is a simple 12 volt regulator. There's another one, that would do it. That would. LM320. All you want is a simple 12 volt regulator, and you want a full wave bridge rectifier. Right, a full wave bridge rectifier, something like one of these. You don't want a big one. Oh, actually, that's 200 volt actually, but it'll be fine. It's 1 amp, which is adequate to run a fan. Right, okay, one of these. Only £1.76, and right, there you go. That way you've got a stable 12 volt supply running the cooling fan, but you need to run your bridge rectifier. Needs to supply the power for the regulator to restabilize the 12 volt supply. Right, okay, so anyway, back to my circuit. You got 12 volts coming in from the bridge, from the regulated supply, and it goes through your thermistors. That you put, sorry, these are the wrong symbols on it, as I said before, because I couldn't find a thermistor in this program. So these are thermistors, and then you've got one on your main input. It's chips. Oh God, I forgot the name now. The oh God, I tell you, I'm getting old. Let's see if I can find it on here. MOSFETs, that's it, the MOSFETs. IRF. Right, let's just have a quick look for power MOSFETs. Right, there's a load of them around. There's different types. Right, okay, so you basically you put your thermocouple on against one of these power MOSFETs in your inverter, and when the MOSFET gets hot, the thermistor resistance drops. As the thermistor's resistance drops, it increases the biasing. It increases the biasing to the BD131 transistor. You could use a different transistor, but you'll have to use different values of resistors, by the way. So it's up to you really. And as the transistor is switched harder on, it conducts more heavily through the collector, and that increases the power through your fan. So your fan speeds up, and that's how it works. Anyway, very simple. Now let's look at some of my old circuits I did before. Now this is what I built before for my solar power to battery protection circuit, something I did a few months back, and it basically uses an op-amp, and it controls the voltage. Basically is cut off to the battery when the battery voltage drops to below a certain point. And I exported this so that there's actually here's a circuit board design I did. Let me just that's it. I need to turn off the layers. Bottom silver screen, top copper. There you go. That's my component layout. Now zoom in a bit. You can see that's my original design. I put some sockets on there for resetting the circuit, and turn the bottom copper back on, turn the silk screen off, and you can see just the basic layout of my circuit. It took me quite a while to get this right. Anyway, the good thing about this software is free, and you can do a 3D representation. So I've got to click on 3D view. You get to see what it looks like, and this is obviously nothing to do with the actual fan controller, but you can see what my circuit looks like, and actually built a couple of boards. That's a representation of the copper. There you go. So you can find this software online. It's Radio Spares. It's called Design Spark. It's free. You can design your circuits on it, and it's pretty generic. Actually, it's basic, because I mean, you can see from the capacitors, and these are variable resistors, and I mean, look at them. There's not even a pop screw thing on it, but it's supposed to be a variable resistor. But it's not bad for free, I suppose. Does the job. But anyway, that's the circuit for the fan. Pretty simple. But you can, if you want, what I would suggest you do, if you want to control the speed of the fan, and when it comes on, you can put a variable resistor in. It should be alright, because it's ground. It's ground there. So I would suggest putting a 10k variable resistor between the base of the BD131 and ground. So if you put a 10k variable pot there, you can adjust the speed of the controller of the circuit, and then you can fine tune it if you want. I didn't bother with that. I just tuned it and tested it in my breadboard. But anyway, so just a variable resistor variable resistor down here instead, and you can adjust the fan speed and that. Okay, I've gone on enough and I'm falling asleep, and it's 2:53 in the morning. So that's enough for me.